So in this video we discuss about modeling in Verilog. So there are different styles in modeling. So just see what are there. So there are the 4 types of modeling styles. So those are behavioral modeling, data flow modeling, gate level modeling and the structural modeling. So most of the people who are studying, they are thinking that gate level modeling and structural modeling are the same things, but meanwhile it's something slightly some difference between the gate level modeling and structural modeling. So we just look into that, what is the difference between the gate level modeling and structural modeling, and in upcoming videos we briefly discuss into the particular thing, means what is behavioral modeling, what is data flow modeling, and in deep. But in this video, so we have to just say what are the things, means how we can represent behavioral modeling, and what is data flow modeling, and what is gate level modeling, and what is structural modeling. Like that we can observe that by using one simple example. So it is nothing but like first we have to look into the behavioral modeling. So by in this video I consider half adder as my example, and by using these half adder I explain the whole 4 modeling concepts. So first of all we can see what is behavioral modeling. So it uses the high level construct like always block and initial block. So when we look into the behavioral modeling separate video, then we look into this what is this always and what is this initial in depth. But until now in this behavioral modeling we use 2 types of blocks, that is always block and it is initial block. So describe what the circuit does. So in this behavioral modeling what it says what the circuit does. So what the circuit works, what is the purpose. So like that in this behavioral modeling we can say like that. So for example if you consider that is like you know that Verilog is in between only module and end module. So every Verilog code is what you have to write, what you want to write. So it is in between the module and end module. So this is the module name. So half underscore adder underscore behavior. So you can use any name, but it is related to circuit design, then it is easily to identify which type of circuit it is and what is the design code, like that. So this is the input, this is the port list, we can say that this is the port list. So in this port list we can give input. So first of all a half adder, what is the half adder? So half adder is like consisting of 2 inputs A and B, whereas sum and carry are the outputs. So let us see, those are the inputs, A and B are the inputs and sum and carry are the outputs. So I can represent sum, A and B are the inputs here, and the output sum and carry. Why we use this range? So just look into that. So in this behavioral modeling we use always and initial blocks. What is the purpose of these using always block means, so whenever your sum and carry will change, means if you consider 0 0 0 1 and 1 0 1 1, so half adder means they are the 2 variables are the inputs, so that you will get 4 combinations. So when your sum changes, so A equals 0, B is equals 0 means sum carry is like that. So 1 0, this is sum and this is carry, this is the inputs A and B. So sum, so 0 1, so it is your like outputs like that. But when your sum and carry get changed, whenever the changes in input, then we get the changes in the output. So how you can represent? So in this always block how you can write means, so you just write always and we can write the sensitivity list. So this sensitivity list represent what it represent means, by for what values. So if any change in A or B, so whether it is the change in A or it can be B. So any change in A or B, so you can get changes in the sum and carry. So you can observe A is not changed but B will change. So then only you can change in sum and carry outputs. So like that these sensitivity represent for which inputs, for which type of variables we can output may be changes. So that's why you can represent here in this sensitivity list. So it can be represent our behavior. So what is the behavior of half adder? So we give inputs A and B, so we can get output sum and carry. So when we get sum and carry, so different values of inputs we get sum and carry. So until the changes in input, it doesn't change in the output. So that's why you can say like that. So whatever the input changes, so I can write these inputs are here. So if you want only my half adder can change only the change in input A means, then we can simply write always at the rate in bracket A. So what it means? So it means only whenever the change in A, we get the change in the outputs. So like that we can represent in this sensitivity list what we can represent. So by considering these changes only, the inside the statements inside the statements which are present in the always block will be changes. So that's why begin. So always block is like this. So multiple statements we can use begin and end. So when we write begin, so we must and should after completion of the statements, so we can end with end like that. So for this module we can end with end module. So it is like behavioral modeling. So it is about behavioral modeling. In next videos we can in depth we can learn about this behavioral modeling. Until then it is like, it seems like this. So it shows the behavior of the half adder. So whenever the input changes, the output may be changing. So it is like this. So next one is data flow modeling. So using continuous assignment with assign statement. So in the previous one, behavioral modeling, we use always block and initial blocks for our necessary according to the behavioral modeling. So in this data flow modeling, we use assign statement. So by using these assign statement, we continuously assign the values to inputs to outputs. So it focuses on the how data flows. So in data flow modeling is just simply say how the data will flow into the inputs to outputs. So again we consider half adder. For your better understanding, I consider only half adder code for 4 types of data modeling, types of modeling. So A and B are the inputs, and whereas sum and carry are the outputs. So here we can observe how the data flows. So how the data flows. So sum, what is the formula of sum? So sum formula is like A XOR B, and carry is like A AND operator with B. So means we already know half adder circuit diagram, it seems like this. So A XOR B means it is A XOR B. So it's in XOR gate is like this. So A and B. So this is AB. So same A and B are the inputs are go to. So this is sum, this is carry. So it is our half adder. So how the data flows. So whatever the expression we have. So whatever the expression we have means for some A XOR B, and in Verilog there are the so many gates. XOR we use like this. So XNOR we can, the symbol is represent like this, or we can represent like this. So for AND operation we can represent like this, OR operation we can represent like this. NOT means bitwise NOT means it is like logical operators and bitwise operators are different. So you can watch that operators video, then you can understand very well. It is said in the previous video. So if you don't watch me, then go into that and then watch and come to this video, then you can understand properly. So logical operators and bitwise operators are different, so don't confuse between this. So here we can see that. So here we can examine again the code is between end module and end module. So there is a module name. It is like module name is nothing but identifier. So by using this module name, we can instantiate these name into other code. Upcoming videos you can see those what is the instantiation, what is the identifiers like that. So input, so what are the inputs? A and B are the inputs. So we can output here. So sum and carry are the outputs. So how in data flow modeling we use assign statement for assign the purpose. So what is the assign states? That means whatever the RHS value, whatever the performance, whatever the equation we can, whatever the operation we can done here. So again what you can done here, A XOR operated with B. So whatever the input A and input B will consider both are X operated, the result will be stored into the sum. So this assign keyword is used to assign these result value to sum. For that purpose we can use this assign statement. So again assign carry, what is the carry formula? So A AND operated with B. So you can simply write carry is equal to A AND operated with B. So this result will go into the carry. So it can end with AND module. So this is, it seems like the data flow modeling. So by using assign statement, we simply assign these to assign statement. So here in this one point is missing like that. So whenever you use this always block, so you must and should represent these outputs with reg. So it not should be while. So while not should output. So always block is only for when we want to assign, means sum, carry, whatever you want to assign. So it must should be reg only. So you have to represent with reg. So don't forget, when we are using always block, you must and should represent the outputs with reg only. Then only your output, your compiler will shows correct answer. Otherwise it shows compiler error. So don't forget, when you are using always block, you must represent here with reg. Otherwise it defaults will take while and it is gets error. So you have to represent reg. Okay. So gate level modeling. So gate level modeling, what is represent using basic logic gates like XOR, AND operation like that. So here we can consider half adder. That's why I can say XOR and AND. But realistically there are so many logic gates. There is OR gate and NAND and whatever the gates we can use anything. So here I consider the example as half adder. That's why I only represent here X and AND. So we can use in this gate level modeling what in half adder we can here see that the example it use XOR gate and AND gate. That's why I represent here. So in gate level modeling in half adder we use XOR and AND gates. So closer to hardware level. So hardware level means it's represented with gates. So it is very closer to gate level modeling is very close nearer to hardware level. So that's why it's say like that, closer to hardware level. So here you can example to represent the gate level modeling, then you can understand properly. So here you can see that it is also a it is between the end module and module. So here we can write the module name here. So identifier. So this is the port list. So in the previous video we can represent how the port list will be represented like this. So what are the inputs? Input AB and output sum and carry. So how we can represent means half adder is seems like this. So XOR gate A and B we get sum here, and AND operation A and B, again this same A and B is written here, and carry we get like this. So this A, this B is give the inputs to AND gate. So this is our half adder circuit. So how we can represent these gate level modeling means, so in gate level modeling we have primitives. So primitives, what is primitives? So they are the inbuilt modules, means inbuilt gates here XOR inbuilt keywords like that. So primitives is nothing but they are inbuilt in this Verilog code. So it has specific performance. So if you write XOR means it consider it as XOR operation. So it seems like XOR operation. We don't use for our keyword. It don't use our variable names like that. So it is a one keyword. We don't use for other purposes. So we have to write this XOR and means they perform XOR operation and AND operation. If you can write OR means OR operation, XNOR means XNOR operation, NAND means NAND operation like this. So these are the primitives. So in gate level modeling we have to see the primitives. So what are the primitives? What are the gates we have? What are the basic gates and what are the basic gates we have? So I can represent those with these names. Then it performs, we must and should represent with lowercase only. So how you represent means, so whatever the gate, whatever the operation gate, logic gate we want to perform, so simply write that. So gate name we can represent with small lowercase letters. So then we can first write the output. What are the output of that gate we can write here, and the inputs. So simply write the inputs. So here what we have to do for sum, we have to use XOR operation. So that's why you can represent XOR, and the output is sum. So whatever the output is we can represent here is sum. So I can write sum here, and what are the inputs? A and B are the inputs. That's why XOR gate, what are the inputs? A and B are the inputs. So that's why you can represent A comma B. So next again carry. For carry, what is the gate we have to use here? AND gate. So that's why AND, and the output is carry, and the inputs are A comma B, and we can close with AND operation. So it is simple way by representing gates. But when you are going to complex circuits, by representing gates it needs for 4 gates okay, for 5 gates okay, for 1000 okay. It's difficult, but you can try okay. But lakhs of gate means it very difficult. That's why gate level modeling is for only simple and basic circuits like that. So look into the structural modeling. So it is slightly difference between the gate level modeling and structural modeling. So instantiation low level modules. So if you want design full adder, so if you want to design full adder, we can use gates. So I can know full adders, they are the XOR gates and like that. So you can use gates and then you can design, but it takes so many gates and so much logic, and complexity may increases. So by using two half adders, also means A, B, C are the inputs for the full adder. So we can simply give the sum and the carry here we get, and the sum and the carry. Again this carry is going to OR operation here. So it is final carry of full adder. This is the sum of the full adder. So again this it seems it is like full adder, half adder we get the full adder. So it is very simple than when compared to we get when you design full adder with logic gates, it takes little bit complexity. But when you are designing with this half adders, so how you can, first you have to simply write half adders code. Then using this half adder code in full adder, you can simply write half adders and then connect with port list. So upcoming video, so in next videos we can discuss how you can write the code using half adders and design the full code like that. So until now here we can represent it with half adder. So the structural modeling means, so you can design one module, so instantiate that module in another module. So it is like the structural modeling. So describe the structure of the design. So it describe the structure of the design in the structural modeling. So first we have to, whatever the half adder design we use, what are the gates we use? XOR gate and as well as AND gate. So you can separately write the codes for XOR and AND gates. So module XOR gate I write here, inputs A and B, and the output for XOR gate they are the inputs, A and B are the inputs, and Y is the output. So I can simply represent input AB and output Y. So assign, what you assign, so what is the operation? Y is equal to A XOR B. XOR gate symbol is like cap, so A XOR B. So I can assign like this and end module. So more than here there is a single line, so that's why you don't use any begin or end statement here. So just simply assign Y is equal to XOR B. So for AND gate, again they are the two inputs, A and B are the inputs and the Y is the output. So again we can represent the module name and the end module. So module name is AND gate and the input A comma B and the output Y. So don't represent it with AND because AND is a keyword, we can't represent it with AND, so you can simply use AND gate. So something, anything you can use. So assign Y is equal to A and B. So what is the operation here? AND operation. So that's why for assigning so output we can assign A and B. So this is one module, this is another module. So by using these two modules we can design a half adder. So this is module 1 and this is module 2. By using these two modules we can design a half adder. So just look, it is also start with a module and end with end module. So you can represent half adder underscore structural. So it is the module name. So these are the port list. So AB are the inputs and sum and carry are the outputs. So XOR gate. So what is this XOR gate? This is the module name of this XOR gate. So first module name. So whatever the module 1 here, so that module name we have to write here. So there is a instance name. So how can write means module name. First we have to write module name. So instance name means we have to represent it by user. You can use any name. Instance name we have right here. So you can use any name, no problem, whatever you can use. So next we have to connect properly by using port. You already say ports connection in previous video. If you don't watch it, just look into that, then come to this video, then you can understand properly. So port connection is the like name by order means position order, means by order we can connect or by name you can connect. So here we can connect by order means whatever the order here, so A, B, Y. So orderly we can connect here. So A is connected to this A means how we can represent means XOR gate is like this A, B and we get sum like that. So this is our half adder XOR gate. This is our half adder XOR gate. So this is the simply XOR gate. So these A is connected to these A. So just I change my color, then you can understand properly. So this is the XOR gate what we have to design in module 1. This is our full adder means half adder. So this is the input A, this is the input B. So these A is connected to this B, that's why you can write A comma B and then this output Y is nothing but our sum. So that's why I simply write it as sum. So these Y, what is the output Y is connected to this sum means this A input is connected to this half adder A. So B is connected to half adder B. So again output Y is our sum. So is not Y A XOR B is nothing but our sum. So I just simply connect our sum. So next AND gate means our carry. So our carry is nothing but AND operation. So this is for AND gate. So for our half adder it like this A and B and carry is our output. So how you connect this input A is our input for half adder A and B and output is nothing but Y is nothing but A and B. A and B is nothing but our carry of half adder. So you can represent with carry. So AND module. So in structural modeling you can simply like this. So you can design a modules by when you are going to the complex modules. So you can use those simple modules in this complex. By that we can simply reduce our complexity. Here you can see within 3 lines or 4 lines so we can complete our design code. But while looking into the complex ones, so it takes hundreds of lines. By using these other modules, so you can simply write in within 20 lines or like 50 lines will reduce us to 20 lines and 20 lines may reduce us to 10 lines like that. So structural modeling is very useful in complex design. So here you can see behavioral is nothing but it is a like high level, easy to simulate. So we can mostly use a behavioral modeling when you want to change our output using according to our inputs. So data flow modeling is medium level and focus on the data path. So how the data flows into the inputs to outputs, we can represent that in the data flow law. And gate level means uses built-in gates close to hardware. So these gate level modeling contains logic gates. Whatever the gates we have, you can implement all these gates in this gate level. So it seems some typical and it is very close to hardware. So structural real hardware design with modules. So here we use other modules and instantiate those modules in these modules. So here we can see this module is instantiated here in this another module. So this is called instantiation. So other module name is used in this module, we can say it as a instantiation. So other videos we can look into the some more coding and everything we can discuss, so then we can understand properly. Until now these are the 4 types of modeling here. So okay, this is the end of our video. So thanks for watching. If you have any doubts you can comment. Until then, bye.